This is section 1.5 part 2. Continuing on with the graphs of functions, we were talking about symmetry today. Things that you've probably talked about before, but again, we're going to kind of go a little bit deeper into what symmetry does for us. So we're still on the essential question of what types of information do graphs of functions give us. And then what we're going to learn today is how to find whether a graph has a certain type of symmetry, while at the same time whether it's odd or even. So may not have heard the terms odd or even when describing functions, but we will discuss that going through this today. So let's first talk about the types of symmetry that there are. We have two types of symmetry. We have lines of symmetry, and you can see from the pictures that you have here and on your notes, a line of symmetry is basically taking an object and cutting it directly in half. So this line of symmetry right here, if you were to fold the triangle over on itself, it's the exact same object. Over on the square, same thing. You fold it over the diagonals, it's the same thing, and over the, if you go through the middle of it, it's the exact same thing. That's pretty self-explanatory. Points of symmetry is a little bit different. Points of symmetry is if we're using a point, say in the middle of this star, a point of symmetry says that if you rotate it a certain number of degrees, in this case from point to point, it would be the exact same image. So the point of symmetry is more of a rotational symmetry, not a line of symmetry. So in pre-calculus, we talk about a few different things for symmetry. We talk about the symmetry with respect to the x-axis, symmetry with respect to the y-axis, and symmetry with respect to the origin. On the x-axis, it's pretty self-explanatory. You see this picture here. It basically means that whatever you have on top is like a mirror image on the bottom, meaning that your values are going to be equidistant away from the x-axis. That's why it's symmetric to the x-axis. And what we say is that for a symmetry over the x-axis, it means that for the x and y that we have, it means that the exact values will work for negative x, for x comma negative y. So in other words, for the same x value, we will have opposite y values. So for example, if our point was, say, 1, 3, then that means that our point that is going to be symmetric to the x-axis here would be 1, negative 3. So the x value remains the same, and the y values are opposite of each other. If we're going to be symmetric to the y-axis, again, you can see very clearly from this picture, hopefully, that that is symmetric to the y-axis. It's a mirror image right over itself. So in this case, we have x comma y becomes negative x comma y. And if we use the exact same point, we have 1, 3, and that would become negative 1, 3. Again, this is just the points that you would have to have for it to be symmetric to the y-axis. So your x values now are opposites of each other, while the y values are staying the same, and you can kind of see that here. The y values are the same, x values are mirror images of each other. And then our last one, with symmetric with respect to the origin, both of them will change. So our x comma y would have a image of negative x comma negative y. So in this case, our point of 1, 3 would also have a point of negative 1, negative 3. Okay, so basically everything is opposite when having symmetry with respect to the origin. So let's just kind of look into a problem or two here and see how this plays out. So in this problem right here, and again, I know that on your paper the equation is probably in a better spot. I'm just going to move the equation down here so you see that. So use the graph of the equation y equals x squared plus 2 to test for symmetry with respect to the x-axis, the y-axis, and the origin. And then we're going to support our answer numerically and algebraically. Numerically will be on this slide, algebraically will be on the next slide. So once you see the graph, hopefully you can see right away this is clearly going to be symmetric to the y-axis. But now let's try and support that. So what we had said was if it's symmetric to the y-axis, then that means that our x comma y would also have to have a point negative x comma y. So let's just take one of the points on here. So let's just take the negative 2, 6. So we're looking at this point right here, negative 2, 6. Based on what we're saying up here, we would also need a point where the y value is the same, but the x value is opposite. So that means negative 2, 6 would also have to have a point of 2, 6. And you can see right next to it there's also that point on this graph. So based on that, that is supporting our answer numerically that we have symmetry to the y-axis. Now, when we're doing it algebraically, this is a little bit different, and this is important for you to know because sometimes a graph isn't given to you, and it's easier to do something algebraically. So we still have y equals x squared plus 2. So again, remember what we're trying to do here. We are trying to, instead of having x comma y, we need to show that negative x comma y is going to give us the same exact equation. Remember, if xy is one of our points on our graph, then that means negative comma y needs to be the exact same point on the graph, meaning the equation has to be the same. So what we're essentially going to do here is we're just going to take the opposite of our x. And this is algebraically. So instead of it being y equals x squared, it's now going to be y equals negative x squared plus 2. And then what we do is we simplify this, and we see what we get. Well, negative x squared is just x squared. Negative x times negative x is x squared plus 2. So because it is the same, that's basically what we're looking for. It's the same, it's the same. So this is proving algebraically that it is symmetric to the y-axis, because when we plug in a negative x into our equation, we get the same result at the end. So let's take a look at another one. Okay, in this case, we have a function xy equals 6. And in this case, we're looking at it, well, if we look over the y-axis, it's clearly not symmetric over the y-axis because there's nothing here. It's not over the x-axis because there's nothing down here or up here. But it does look like maybe we might be symmetric to the origin. So let's take a look at this. So we know that symmetric to the origin means that we have to go from x and y has to also have a point opposite of x and opposite of y. So let's take a point on our graph and see if that works out. So let's just do the first one here. We have negative 3, comma 2. So if we have negative 3, comma 2, then that means another point on the graph should absolutely be 3, comma negative 2. And right next to it, you see that that's our point. So that proves numerically that we have symmetry over the origin. Okay, now once again, we're going to do the same thing algebraically on the next slide. We have our equation, which is xy equals 6. And we know that if it's xy is our point, then that means we should be able to plug in a negative x comma negative y and get the exact same thing. So let's try that. Negative x times negative y equals 6. Negative times a negative is a positive, so we have positive xy equals 6. Same equation, so that proves that we have symmetry over the origin. And that's basically what you're doing algebraically to show the symmetry is you're either, if you want to show algebraically x-axis, then it would have to be x comma y and x comma negative y. If it's over the y-axis, it's got to be x comma y, negative x comma y. And then if it's over the origin, it's got to be negative for both of them. And again, all you're doing is plugging those in for your variables and making sure that you get the same equation. Because if you get the same equation, then you know it falls on that line, and that's what we're looking for, is to see if these points that we have to have based on symmetry are actually falling on the exact same line. So now let's, this kind of is a segue into determining whether functions are even or odd. So the one thing we want to make sure that we understand, all functions are not one or the other. They can be neither. So it can be as a function odd or even, but it also can be neither. Very, very important for you to understand that. A lot of functions, most functions are neither. So in this case, an even function simply means that when we plug a negative x into our function, we get the exact same result. So essentially, an even function would be symmetric to the y-axis. Okay, so if you have symmetry over the y-axis, you typically are going to have an even function. Okay, and then an odd function, this one's a little bit different, but in this case, when we plug in a negative x, we're going to make our entire function negative. So that doesn't necessarily mean that you're symmetric to, you're going to be symmetric to the origin in this case. So we have symmetric to the y-axis is even, symmetric to the origin is odd. But remember, not every function has to be one or the other. You can have neither if it doesn't work out. And it makes a lot more sense when we actually look at the example. So let's look at the first example. We have f of x equals x to the third minus 2x. We want to find out, is the following odd, even, or neither? So immediately, the first thing that I do is I plug in a negative x for my function. So I put negative x to the third minus 2 times negative x. And what we have here is we get negative x to the third, because the negative to the third power will stay negative, and the negative will turn into a positive. So we have negative x to the third plus 2x. That is not the same as what we have up here, so we know for sure that it is not even. Now we got to check to see if it's odd. Well, hopefully you notice that everything is opposite in this problem. Notice the positive x to the third went to negative, the negative 2x went to positive, and in the same way we could factor out a negative here and be left with x to the third minus 2x on the inside. So you see the x to the third minus 2x is the same as it is up here. We just now have a negative out in front. So that means that our f of negative x is actually equal to negative f of x, meaning the whole thing just becomes negative. So plugging in a negative x gives us a result of negative f of x. Therefore, this function must be odd. And these ones are usually the most difficult for students to figure out, is understanding what it means to put in a negative x and get a result of a negative f of x on the outside. Remember, you're just basically taking your function and making it completely opposite, making it totally negative. So what you essentially want to do is once you plug in that negative x, if it doesn't look the same, you want to factor out that negative and see if what's left over on the inside of the parentheses is left over. Okay, so that is an odd function. So let's look at another one. So we have x to the fourth plus 2 here. So when we plug in our value here, again, we always start with just plugging in negative x. So we get negative x to the fourth power plus 2. The negative to the fourth power will become a positive, so it does become x to the fourth plus 2. You notice that we have the exact same function that we started with, which defines an even function. So in this case, we have an even function. Okay, let's look at the last example. Here we have x to the third minus 0.5x squared minus 3x. So once again, plugging in a negative x, we get negative x to the third minus 0.5 times negative x squared minus 3 times negative x. This first one will stay negative because of the third power. This middle one will become positive, so it's going to stay as a minus 0.5x squared. And this last one will become positive. So you can see that it's not the same as it is up here, so clearly it's not even. But let's see what happens when we factor out the negative if it ends up being negative, or if it's completely the opposite. So we pull out the negative and we end up with x to the third plus 0.5x squared minus 3x. So you can see it's almost the same, but it's not completely the same because this middle term is not the same as this middle term. So in this case, it's not even or odd. So in this case, we would just say it's neither. So hopefully that makes sense. That's all we're really focused on in this section is the symmetry and the even or odd. So I will see you in class and just bring questions there.